Oh, good. Okay, sure. Yeah, I may need it. Maybe you can start live stream. Oh, you've started. Okay, good. Okay. Okay, cool. Thanks. Okay. Setup time overhead. Okay, let's get started. Can people see this from the back? Wow, you have good eyes. Okay, I can barely see it from here. Okay, welcome to a seminar in computer architecture. Hopefully you're excited about it. Okay, good. How many people here have taken DDCA? Okay. How many people here have not taken DDCA? Okay, that's good. We have a mix. How many people are in CS bachelors? Probably you've taken DDCA then. Okay. How many people are in ETET? Bachelors? Okay. Bachelors? No. Masters? Okay. How many people are in CS masters? Okay, so we have a good mix of. How many people are PhD? Okay, other than the TAs, of course, people are taking the course. Okay. Okay, cool. Welcome, everyone. It's good to have a good big mix of students. The seminar always attracts across the board. Sometimes PhD students also take it. Okay, but we're going to have fun in computer architecture. So hopefully that's why you're here. Let me introduce myself. I think I see some familiar faces. But how many people have taken, I guess, DDCA from me? For those of you who've taken DDCA from me, of course. So I see a bunch of fans, but not everyone. Okay, because I was on sabbatical last time it was taught, so you may have taken it. Okay, I'm Onur Mutlu. I'm a professor here for some time now. I was a professor at Carnegie Mellon University before this. And before that, I was at Microsoft Research. I started the computer architecture group there, did a bunch of interesting things. I'm still doing interesting things, at least from my perspective. It's exciting, actually. We may see some of those, not today necessarily, but during the course of this seminar. Before that, not before that, but before that, I was a PhD student at Texas. But during my career, I worked at a bunch of different places like Google, VMware, Microsoft, of course, Intel, AMD, and I spent my sabbatical at Stanford recently. And before that, I was in your shoes doing my bachelor's, most of your shoes. Some of you are doing your master's, but I did my bachelor's in computer engineering and psychology from University of Michigan a while ago. And I wish I had a seminar course reading papers, because when I read my first paper at the University of Michigan, when my to-be PhD advisor gave one of the papers, I didn't understand anything at all. It was a tough experience. And that's a not so hard paper right now, of course, or even after 2 years or so. But once you get used to reading papers, I think it's fun. And it's a good experience to critically analyze and read papers. This first part of the lecture will be kind of an introduction. If you have taken a course from me, you've probably seen part of it, but I'll still go relatively quickly. I don't want to keep you here for the entire 2 hours. I do research and teaching in computer architecture, computer systems, hardware security, bioinformatics, and I'm interested in everything essentially in architecture, and we're going to see some of that today. But before that, I should introduce my co-instructors. Mohammed is in the back. He's a senior researcher and lecturer in my group for some time now. Even before that, he was a visiting PhD student in my group. He got all of his degrees at Sharif University of Technology at Iran, a top school over there. And you can reach him. Well, you can reach me also with my email. And you can reach him with that email. He's doing research in a lot of areas that my group works on, as you can see. We also have another instructor, Konstantina. She's sitting right over here. She is also a senior researcher and lecturer in my group. I don't know if this is completely correct. Head teaching assistant. That doesn't sound correct. I think we can change the slides because you're an instructor. And she got her PhD from NTUA in Athens, which is a top school in Greece. I guess maybe arguably. I know some people, some other people are here, but it also depends on who you ask, I guess. Okay, but it's a great school. Yeah. And she did her PhD on accelerating bioinformatics workloads. And she also does a lot of research on different areas. So you can contact us anytime. This is the group that you will be seeing. Some of these folks may be your mentors. It's an old picture, so maybe your mentors are more likely here. My research group will mentor you during this, because you will see that you will present papers and there will be mentors assigned to you who will help you make your presentation and delivery better. Does that sound good? You can learn more about them online. We do research in computer architecture. You can learn more about us online. I'll go through these relatively quickly. We have a bunch of PhD and postdoc alumni that we're proud of. There may be more coming soon. You can learn more about them also. Some of them are actually TAs in this course who mentored other people. Now they're professors or researchers somewhere. So we have a lot of material online. You can learn more about us that I will not talk about. But I will talk briefly about this because this seminar is, in my opinion, about really what we do research in as well. But we want to enable fundamentally better computers going into the future, because computing is really at the heart of everything we do. And it's going to be more and more so going into the future, in my opinion. And we need to design much better computers. And hopefully in this course, you will see different ways of looking into how to design computers and how to design systems. And we do a lot of research in this area, and you can learn more about that. So there will be some papers that will talk about processing in memories, for example. These are some new paradigms. There will be some papers that talk about different sort of accelerators to make machine learning or some other applications better. There will be some papers on memory and storage. You will get to choose what you present. At least you'll have a say in it. But we will assign you the papers based on your preferences at some point. Does that sound good? Okay. So these are some areas of research. Again, I don't want to keep you here for long, so I will not go into details, but these are some exciting areas that where we may read papers in as well. I will, I guess, maybe quickly mention that robustness is a big issue in designing computer systems today. Energy is a big issue. You may have heard about it, especially with these huge AI models that people waste a lot of money and resources and the world's water and climate on, let's say. And if you don't have good energy efficient architectures, we're going to waste more and more. Latency and predictability are important. Making architectures more intelligent is important. And designing architectures such that we're much more efficient overall for different applications is important. And these are areas we do research into. I will mention this because I think this is very important. Traditionally, computer architecture is viewed as the interface between the hardware and the software and the underlying microarchitecture that implements that interface. This is ISA, instruction set architecture, and this is the microarchitecture. But in this course, we'll take a broader view. So you will see papers that are not just confined to this part. We'll actually take a broader view as is happening in industry as well as research. We'll really cover from algorithms to devices. So there will be hopefully some interesting papers that you will present and read and discuss, critically analyze, that may take an algorithm and adapt it to some underlying device by changing the logic, etc. And this is important today because we want to really optimize for high performance, high efficiency, high reliability. And it's very difficult to do that without this sort of co-design. If you don't take into account the algorithm and adapt it to the underlying architecture and maybe change everything in the stack, which is of course not easy to do, but change some things in the stack such that you can better communicate from the algorithm to the devices, you don't get the highest energy efficiency and performance. So that's why we are doing it, and other people in industry are also, let's say, doing it. So this is actually a quite research-oriented course, but it's also a teaching course. And I like this course because we cover a lot of papers, and it's kind of my philosophy in teaching to discuss research a lot. Because these are, in my opinion, two sides of the same coin. You do research, which is something that you discover something that nobody else knows. And at some point, you need to report your results. Now you educate the community, it's teaching. And after that point, that research that you've done is not new anymore. It's really part of the teaching domain, it's education, right? And I think teaching new things enables new research, and teaching fundamentals also enables new research. And new research enables teaching. So this is a virtuous cycle, if you will, that never ends. Does that sound good? That's why I'm passionate about both of these, actually. So we have a bunch of other courses. If you have, well, some of you have taken DDCA. DDCA is a pretty basic. It's a bachelor's course that's required for CS students. So if you've taken DDCA, actually you have, and if you enjoyed it, you have a good background for this. But we have also some other courses like Fundamentals of Computer Architecture that we've introduced recently for mainly electrical engineering students. And I see some familiar faces from that course over here. And also like more advanced computer architecture courses. So if you like this course and if you want to go into even more advanced computer architecture, I would suggest taking computer architecture that we offer in the fall. We do a lot of open source artifacts. I want to mention this because I think this is really important right now. It enables research to actually have impact more quickly and also enable other research and also teaching. And you can find some of the things that we release online here. But you will see in the papers that this enables reproducibility, of course. It's good scientific practice, I think, in general. But you will see in the papers that you read, this may or may not be the case. So it's good to think about that also. Okay. Well, I also mentioned that. I think in this course especially, we're going to talk, like whenever you analyze papers, it's always good to analyze what is the key contribution of the paper, right? I'm going to give you later an analysis methodology. It's good to focus on insight. What is the insight that this paper brought into the field at the time it was written that people didn't know? It's good to ask that question because that's probably the most important contribution of the paper, right? The insight may be a new problem, right, that no one has thought about. The insight may be a new mechanism. It may be a new concept. But this is what really enables a better world, in my opinion. This enables new ideas also. So clearly, it's a paper reading and presentation course. Learning and scholarship are important. And these are some values that I really care about. And I just want to share them with you. And hopefully, we will have this in this classroom also, because we would like to discuss ideas very openly. And we would like to collaborate together when we're critically analyzing papers. So I would like people to participate in general. So there will be some presenter who presents a paper, but please participate so that we get the best out of that presentation so that everyone learns. Okay, I believe that quality is important. I'll go through this relatively quickly also, but you will see, I think, maybe these will become more clear when we talk about some papers. You will see some papers, for example, that have had a lot of impact, and people follow their passion to enable that work, right? And that work may have made a huge difference in the world, like we just covered in Fundamentals of Computer Architecture, some out-of-order execution ideas. Those papers, when they were being written, a lot of people were extremely skeptical. And they had very fierce criticisms saying, for example, if you actually do out-of-order execution of instructions, if you've taken DDCA, you would know out-of-order execution very well. If you don't know, basically, you execute instructions in out-of-order. If you do out-of-order execution, this is too costly, too much hardware. Nobody wants to spend that hardware on anything. We're talking about 1970s, 1980s. Now everybody does that. Right? Why? Because some people really followed their passion and they said that this is the right thing to do to get high performance, and we're going to figure out how to do it. Initially, it was not extremely efficient. Still, it's not extremely efficient, but it's much more efficient over the course of many years. Now, all processors implement out-of-order execution, all, let's say, very interesting ones. Yeah, okay. And people have built infrastructures to enable that also. So I think I liked going through this. Whenever you read papers, think about what went into the work also. Don't just think about the paper, the idea, etc., but what went into it, right? There are some works that actually require a lot of infrastructure to be built from scratch. And those enable very interesting results in the end. And some of this may need to happen as a collaborative effort also, right? Okay. But all of these require hard work in the end, I think. Okay. Okay, I'll stop here, but I will refer you to, how many people have read this paper? Okay, because you've taken computer architecture, I know, because I asked you to read it over there. But this is a nice, it's not a paper actually, it's a transcript of a seminar that Richard Hamming delivered at Bell Labs at some point in his life. How many people know about Hamming? Nobody? Some people know about Hamming. Hamming distance, Hamming codes, etc. He did a lot of work on coding theory. He's actually considered one of the essentially people who started that field. And error correcting codes, a lot of them are actually based on Hamming's work. But this transcript, I recommend people to follow because he has a lot of good suggestions, I think. Most of them I agree with, and this is him. As a researcher, basically, if you want to be a first-class scientist, you need to know yourself, your weaknesses, and your strengths. and make your defects become assets. It's not easy to do, but he gives examples from himself also, like he has some egotism, for example, and he tries to make that into an asset. So basically, I think he also analyzes why many people have greatness in them, but unfortunately they don't succeed because they may not work on important problems. And I actually agree with this. I think a lot of people are very capable, but they may choose to work on something not so important. It's important to work on important things, I think. Or they may not become emotionally involved, meaning they may not have the passion to solve the problem in a way, etc. Okay, so basically saying it's not just luck. It's also your passion, your choice of problems, as well as how you approach it. Okay, I would recommend reading it. This is just a summary of 2 paragraphs of his speech. Any questions? Okay, the role of this course. Well, you've seen the slide in DDCA and maybe some other courses, but you're here for computer architecture, maybe learning more about it, broad view of computer architecture. It's really the science and art of designing computing platforms. And we're going to really take that broad approach when we select papers. Actually, we're going to give you a set of papers to choose from, and you're going to give us your rankings, and then we're going to decide who presents what. And the goal in computer architecture is to design this computing platform to achieve a set of design goals. It could be a supercomputer, for example, highest performance on LLMs. That's what everybody wants today. Maybe not the best thing in the longer term, but that's one thing that is hot today, clearly, right? But this is kind of supercomputer, right? This is the supercomputer mentality. It could be other workloads also, right? It could be a mobile computer. You want to get the longest battery life at a form factor that fits in your pocket with cost less than some amount with some acceptable performance on workloads you care about, right? This is like a cell phone or smartphone today, right? It could be a more general purpose computer. You want to get the best average performance across all workloads that you target at a reasonable performance cost ratio. This is like a general purpose computer that kind of looks like this, right? And there could be many things. In the end, these are actually all part of computer architecture. You design the hardware, you design the interface, you design the system software, you design the programming model. Especially if you want to get the highest performance, you really need to design across the stack. If you're more general purpose, maybe you don't change too much on the software levels, but you actually change the hardware and maybe once in a while the interface, right? So basically, many fundamental principles are similar. And these are some computing systems. I will not go through this in detail. This is my favorite picture, as you may know, from DDCA. So we have a lot of interesting computing systems today, self-driving cars, and people design processors for it. A lot of them use like machine learning and vision processing, etc. And people build data centers. People build supercomputers. This was one of the fastest supercomputers of its time. This is another one. This is machine learning accelerators. We may read papers about some of these things, both implementation and concepts. GPUs, more GPUs. Clearly, they're hot today for some reason. But they're hot not just because they're computation engines, but also memory. They have high bandwidth memory, and we'll talk a lot about memory also in this course. But they also have interconnect. This is just a fancy picture of the NVLink interconnects that they have that keep getting more and more efficient and higher bandwidth, because you need communication across many GPUs to solve large problems, right? And that communication comes by having links between GPUs and memories that are connected that you can access at high bandwidth. Okay, clearly there are some things that are driving these GPUs also. Okay, we're going to talk about not just let's say compute units, but we're going to talk about interconnects, etc. So hopefully people will choose interesting topics across the board so that we can have a good, interesting selection. People are also building systems that look like this. This is a wafer scale chip. This is probably a better picture of it. This is a real person holding that chip. It's a nice chip, right? You can carry it in your pocket. Maybe not. It's designed to basically accelerate machine learning inference, especially to be faster. And again, you can connect these things together so that you can solve larger problems. Except this is expensive, and there are a lot of interesting issues over here which we're not going to get into, but we may read papers on wafer scale processors, for example. This is an area of research that people are dealing with. There are also chips that look like this today. These are just examples to give from real systems. These are memory chips that can also do computation inside them. Normally, memory and computation are kept separate, but people have been designing memory chips that can do computation recently. This is one company, UpMem. And the other companies have also been designing memory on top of computation units. For example, this is 3D stacking technology. So you can stack different dies on top of, let's say, a logic die. And you can do computation next to memory. In this case, they wanted to accelerate matrix multiplication, for example. They do simple operations, multiplication, multiply, and accumulate on the logic die. And there are other chips that look like this that I will not keep talking about. But there are interesting things happening today, actually, in industry, which is good. But we're going to look at, we may read some industry papers. We may read, a lot of the papers we're going to read are going to be academic papers. But there's also a lot of collaboration that goes on between industry and academia in this area. Okay, there are also interconnects that enable pushing computation to somewhere else other than the CPU today. Okay, so processing in memory is very interesting, and hopefully we'll read some papers and analyze them critically. Okay, I think you've seen some sort of it before since you're in this course. I'll go through this relatively quickly, but essentially there are many benefits of studying computer architecture, because I think a lot of the things that you have seen enabled things like GPUs, for example. At some point, they were used for graphics. Today, most of their use is not just for graphics. It's really for machine learning, right? So they evolved. They're enablers because some folks figured out that they could parallelize matrix vector multiplication really nicely, and this fits the deep neural networks. This was papers in 2010, 2012 from University of Toronto. So this is good, right? This is interesting. So clearly, these computer architectures have enabled the machine learning revolution. So don't underestimate the hardware layers. So you can enable better systems, enable new applications, enable better solutions to problems, and if nothing else, maybe understand why computers work the way they do. And today is a very exciting time because there are many difficult problems we're facing, both at the problem level and application level, as well as the design level of hardware and the devices. And again, you will see different examples of this. I don't want to enumerate all of these here, but when you're reading the papers, think about like what kind of problems that this paper is solving. And it's always a trade-off. If you've taken DDCA, there's no idea that has only upsides. And there's no idea that has only downsides in general. So you need to actually analyze things critically. For example, you may be actually solving some of the problem by making some other problem much worse. Right? The key is basically finding a trade-off point where you solve most of what you want while not making some other things too bad, right? Okay. Yeah, basically we will cover fundamental and cutting edge research papers in computer architecture. We'll have a mix of those that you can select from. And we'll have multiple components in this course that are aimed at improving your, hopefully, technical skills by learning more about computer architecture and also discussing it. Critical thinking and analysis. This is really important because when you read a paper, you're supposed to critically analyze it. And for that, you need to critically think. This may require you to read more papers also in the process. Technical presentation, that's another skill that you don't normally exercise in many courses, but the purpose of a seminar is really for you to get up here and present. Hopefully that'll be fun. My first presentation, I was pretty scared. It may be your first presentation. For whom it would be the first presentation ever in front of a group of people? Okay, so a lot of people. So hopefully you're going to have fun. Don't worry. And then in both spoken and written forms, because we're going to ask you actually to fill out a form later on. And hopefully this will familiarize you with some major research and design directions in architecture. And you will see more. Maybe there are other things that you will gain from this course also. So the key goal is really to learn how to rigorously analyze, present, and discuss papers and ideas in computer architecture with the broad definition of computer architecture. Now, to achieve this key goal, both the presenter and participants are expected to do something. So there are some steps. For the presenter, they need to read the paper that they're going to present. They need to absorb, maybe read more, do some literature survey, critically analyze, think, and synthesize, and prepare a clear and rigorous talk, and then present. During the presentation, answer questions, and also engage the audience so that you can do better analysis. I didn't add that over here, but as a presenter, your goal is also a discussion leader. So you want to guide the discussion by asking questions and also answering questions and steering the discussion. And in the end, you analyze and synthesize because we have a synthesis report. Actually, that's true for everyone also. And the steps for the participants are essentially discussing, ask questions, maybe generate ideas, and again, analyze and synthesize. Does this sound good? Okay, you'll see examples of it also. So there will be many topics. This is just a brain dump of some topics that came to my mind at some point in time. We may have other topics also, but I think hopefully it'll be exciting. This is in no particular order. It just happened to be in this order. So hopefully we'll see a lot of interesting things. So basically, hopefully this course will enable you to think critically and broadly, because we'll cover a broad range of topics as much as we can. Let's see, because this is also dependent on the selection of the papers. And I already said a lot of this, I think. And also, I think reading papers is one way of getting into research. If you've not done research before, but you're interested in it, reading papers helps you get into that. That's one of the steps to do research. Because you get familiar with key research directions, or you also figure out what not to research, potentially, right? And also, so you figure out like what is interesting, what is not interesting, and also what kind of paper may be good to write and not good to write also. The fact that a paper is published doesn't mean that it's necessarily a good paper in the sense that well-written paper. Some of the papers may be very hard to understand. Okay, so this is my virtuous cycle of scientific progress. You start with reading and critiquing papers, understanding problems. That's what you would do in this course. And then you question, brainstorm what you would also do in this course. And then maybe in this course, you develop some out-of-the-box idea. It's potentially possible, right? When you're analyzing a paper, you say, oh, I have a much better idea. Then you develop that idea, and then you figure out someone else did it. That's usually the case in general when you first develop ideas. But over time, you figure out, okay, you get closer and closer to the cutting edge, and you develop ideas that are not done. You may be able to develop an idea that's not done off the bat, but not so easy always. Okay, now outside the domain of this course, you actually do some research and collaborate, work hard, and maybe write these papers that is going to be read by seminar students 20 years down the road. Does that sound good? And then they're going to do the same thing. Or you're going to do the same thing. You can do that also, right? This could be your cycle. This could be collaborative cycle in a broader picture of many people, right? Okay, I like this. If the cycle is broken at some point, that's not good, probably, right? Of course, you can develop new out-of-the-box ideas without doing anything over here, but it makes it a bit tougher. At some point, you will need to figure out whether your idea makes sense or not. Okay. So we've said some of these things. I'll go into a little bit more logistics. We've introduced people. There are also a lot of TAs. I think this also needs to be corrected. Konstantina, you're everywhere on these slides. Yeah. Yeah. Okay, you can fix it. But basically, the TAs are going to be my students. How many of them are here? Can you raise your hands? Okay, you see a good number of them, maybe not all of them. They're going to be your mentors at some point, and we usually try to match the topic of the paper that you choose to particular mentors. You may actually be reading papers that are written by some of these folks, or they may have significant expertise in the area. Depends on the paper, of course. So this mentorship, I think, is very important, and this is the feedback that we've gotten in the past a lot. People learned a lot through the iteration that they have gone through, the iterations they've gone through to make their presentation better, because they had to discuss with their mentors quite a bit. I hope people are looking forward to that. Okay, good. So, okay, these are some expectations and requirements. I normally don't require attendance for my courses, but here, this is different. This is a seminar course, and I would like to require attendance. If you cannot make it, let us know. We're not like, if you don't come here, you get a 0 grade. If there are conditions where we're clearly flexible, but so there will be cases where people may not be able to make it for some reason. But you can also join online, right? So each student will present one paper. As I said, we're going to talk about this more. Non-presenters are expected to participate, ask questions, contribute thoughts. This is better if you actually read or skim the paper beforehand, of course, right? But of course, it's I don't expect everyone to read every paper in this course. But skimming paper is actually a good skill to have also, right? If you're a good skimmer, you can actually get a lot out of a paper without reading it in detail. But sometimes the devil is in the details, and you may miss those devils even if you're a good skimmer. Okay. So non-presenters take an online short quiz after each session. We still have this, right? Okay, good. 3 multiple choice questions for each presentation, and you'll have 1 full day to submit. And this is part of your grade. And I don't know if we still have the online review system, but that has not been very successful in the past. We have it. Okay, good. If you use it, that's good also. And at the end, you'll write a synthesis report synthesizing everything you've learned. This is required to pass the course, and we have a sample synthesis report online. Okay, this is the course page. All course materials are posted there, including some of the assignments that I'm going to talk about. You can check this or your email. Actually, checking the course page is better than your email, I would say. There's Moodle. So feel free to discuss anything related to the course, and quizzes will be there, multiple choice. Paper discussion will be there. Your assignments will be submitted there. Okay, so we require you to submit homework 0, which is an easy one. It's basically information about yourself. If you don't submit it, then you can get a 0 grade. But it's going to be easy, so don't worry. We just want to learn about your background and what you do. Okay, but this is important because we want to schedule people for presentations, and we want to receive these first. But there's time, as you can see. There's also 1 homework just to get you, let's say, warmed up. A short review, a critical analysis of 1 paper. And you can find this online also. This is all up to date, right, online? So if I click this link, the homework will appear. Okay, you can do that. I don't try it. I don't want to try it right now. Okay, so it's mandatory to submit the review because this will get you into the, let's say, warm up. It'll warm you up essentially. And then we will later tell you, we will prepare a list of papers that we would like you to, let's say, choose from, give us a priority order from, and you will have a due date for that. Please don't miss the due date for that, because this is important to schedule all of the presentations for the rest of the semester. Again, you will learn more about this. And then in the end, usually 1 month after the last lecture, you will submit a synthesis report. But you can submit it earlier, of course. And you can actually find the synthesis report right now online. You can have a good idea of what's in there. It's basically for you to analyze the entire course, what you've seen in the entire course, and put the paper that you presented and other papers that you've seen into perspective of the entire course. And I think this is very useful because otherwise this course is just I present a paper, well, you present your paper, get some feedback and participate, but never get the opportunity to synthesize globally what may be happening. Okay. Any questions? Okay, so now let me talk a little bit about how to deliver a good talk. I mean, you will see examples, so I don't want to actually be extremely didactic about this over here right now, but the best way of looking at it is probably seeing examples of slides, which we have plenty of from past semesters, and examples of talks, which we also have plenty of on YouTube that you can watch. But basically, these are some things to have on the first slide, and your mentors will hopefully help you also. Usually it's good to summarize the paper with 1 slide as much as possible. What is the key problem that the paper is trying to solve? What are the key ideas? What are the key mechanisms? If it makes sense to talk about the implementation, is there something over there? What are the key results and key conclusions? And always think, what is the key fundamental insight that this paper has contributed, right? You can start with that perhaps, right, actually. And then the analysis, all papers have strengths and weaknesses, as we talked about, right? All ideas have strengths and weaknesses also. You talk about the strengths and you order them based on importance. And usually, for example, the paper is written badly is usually probably the not biggest strength. Well, the paper is written well. It's probably not the biggest strength. If that's the only strength of a paper, then probably it's not a good paper, right? It's so basically it's introduces this new idea that's now implemented in all processors, for example. That's the big strength, right? Out of order execution, for example. Okay, so here you need to think critically, but in weaknesses, you think even more critically, because every paper and idea has a weakness. And this doesn't mean that the paper is necessarily bad. In fact, many good papers that try to move the needle significantly in an area, sometimes they overlook things, either intentionally or unintentionally, because they cannot solve you cannot solve everything in one work, right? But this doesn't mean that the paper is also completely perfect. So you need to identify the weaknesses of papers also, right? For example, the out-of-order execution papers in the past, they didn't talk a lot about complexity, right? Because that's not what they were concerned with. The goal was to really, we were talking about again 1980s. The goal was to actually show that this paradigm of execution can buy you a lot of performance, even in existing code. Now, if your goal is that, maybe you don't need to go all the way to actually quantify the complexity of that, right? Especially in 1980s, because things were not that open also. Today, things are a little bit more open and accessible. You can do that much more easily today, right? If you have a new paradigm, you can perhaps more easily implement it today and prototype it in some way. So it's also good to think about the time frame at which the paper is written. A paper that's written in 1950s is very different from a paper that's written in 1980s, very different from a paper written today in 2025. Both because the knowledge base on top of which the paper builds is very different, and also the base with which evaluations can be done is very different, right? In 1960s, 80s, even 90s, evaluation methods were actually much less, let's say, much less available in general to researchers. Today, we have a lot of open source software and hardware. Right? So you're lucky in that sense today. You can do a lot of things with open source hardware and software, but that was not the case a long time ago. Okay, basically, this is where you should think critically, because papers may not also talk about their weaknesses. Papers are in general very good at talking about their strengths. Well, they don't maybe not explicitly talk about that also, because some of the strengths you need to synthesize based on what has happened since the paper was written. But weaknesses are usually not talked about because, well, there are multiple reasons. One is you don't want to highlight the weaknesses in general necessarily, right? Because you want to show the benefits of an idea, and weaknesses may be solved later, right? If you highlight too much of the weaknesses, then 5 years down the road, somebody solves it, and your paper keeps highlighting the weaknesses, right? Doesn't make sense. And maybe you're going to work on those weaknesses, right? So it's good to actually think about that. But when you analyze a paper, it's good to think about both. And then here where you can brainstorm, what are your thoughts and ideas? Can you do better? And then takeaways. And then discussion starts, then questions for other people. Does this sound good? You'll see a lot of examples of this, but this is one example of an executive summary from one of my students, Girai's papers at DSN in 2022. These are examples of good executive summaries, I think. Another example from Minesh's paper. So this is what is suggested, but again, you can see examples of this. Basically, a good presentation is probably summarizing the paper, including all of these over here, in 15 to 20 minutes, and then has maybe a 10-minute critique of the paper, strengths, weaknesses, maybe alternatives, new ideas, and then it jumps into discussion. So total, I expect a presentation will last about 50 minutes or so in total. Less than half of it is probably best spent on summary, and hopefully a lot of it is spent on critique and discussion. Does that make sense? Okay. There's more advice over here. Be very critical, because this is actually good for both analyzing the paper and also good for developing new ideas. If you're critical, then you can come up with much better ways of solving the problem. Now, this is related. I always think about better ways. Question the problem as well. Is the problem still relevant? Is the problem solved? Is the problem actually, does the problem make sense? If the paper has a problem with the problem, then that may not be a good paper. But it's always good to have an open mind as well, because the problem may not be exactly what the paper envisioned, but the problem may have evolved also. So it's good to have an open mind. Okay, reading background papers helps, of course. Okay, this is actually how things progress in science and engineering, and how you can make big leaps by really having this critical mind and always trying to push or move the needle by thinking about better ideas. Okay, so we have some few sample texts provided online. Any questions? Otherwise, I'll get into rat holes. So these are rat holes. Rats live in holes. But that's not the purpose of this picture, to show you the rats. Essentially, rat holes happen in discussions. And we should avoid the rat holes as much as possible. For example, when people present, sometimes people may harp on some things. It could be, oh, okay, this paper didn't examine workload XYZ. You could do this for 1 million workloads, and then the discussion will be only about workloads. Right? That's probably not a very fruitful discussion. It's good to acknowledge that, okay, this paper targets workload X, let's move on. How does it work on workload Y? That may be interesting, may or may not be interesting, depending on the topic. Metrics, this paper evaluated X, didn't evaluate Y. Okay, let's not go into a huge discussion on that. It's good to finish that discussion. Configuration, basically, these are rat holes that are triggered in a lot of performance type of discussions. And computer architecture is a very performance-oriented field. You always want to improve performance, energy, or some metrics, let's say. And you can basically poke holes in any paper in all of these. So poke holes, but don't spend too much time on those holes. Does that make sense? Unless there's a critical flaw, of course. But again, when you find a critical flaw, what can you do about it? Talk about it for 30 minutes? Probably not a good idea. Talk about better ideas or how to solve the problem, right? Okay, this is a better way of looking at the rat holes, because from this book that I like. Usually workloads are the biggest rat hole, actually. And then performance criteria, metrics, configuration of the like evaluation methodology, and some details. Okay, this is from this book, Acknowledge. It's a beautiful book. If you've done some performance analysis, I'd recommend this book. And this is the picture over here. I will we'll take a break in a little bit, but I'd like to read this because I think I really like it. And also I think it's good, it's instructive. Rod Jane calls it the decision maker's game. So he says, even if the performance analysis is correctly done and presented, it may not be enough to persuade your audience, the decision makers. This is good because when you deliver a presentation, your goal may be to persuade the audience, right? To follow your recommendations. The list shown in box 10.2, which is in the next page, is a compilation of reasons for rejection heard at various performance analysis presentations. It could be any presentation, but he's focused on performance analysis given the subject of the book. You can use the list by presenting it immediately and pointing out that the reason for rejection is not new. I like this. It's very proactive, right? That's what I did earlier. The reason for rejection is not new. So let's move on and discuss something else. And that the analysis deserves more consideration. Also, the list is helpful in getting the competing proposals rejected. So you can use it for your own purposes. Of course, it's tongue-in-cheek, right? And I like this because he continues saying, there is no clear end of an analysis. Any analysis can be rejected simply on the grounds that the problem needs more analysis. So keep this in mind. Basically, you can never be satisfied. But sometimes you need to take the leap of faith and do it, right? Well, so for example, one option is you're building a new processor, new system. How do you decide when you actually commit to building a particular system, right? You can keep demanding new analyses, and then you will never build a system. Or you can say, at some point, this is enough. We're going to build the system, and this is how it's going to look like. If you never take that leap of faith at some point, based on the analysis that you've done, then you'll never build a good system, right? This is very similar to writing a paper also, right? You may want more and more analysis to write a paper, but if you, at some point, if you don't say, this is enough, I'm going to write the paper, you'll never write the paper. Okay, so you can apply this to many things. Okay, let me read more. This is the first reason listed in box. The second most common reason for rejection of an analysis and for endless debate is the workload. Since workloads are always based on past measurements, their applicability to the current or future environment can always be questioned. It's actually very irrelevant to computer architecture, because when people design processors or computer architectures, they're used, maybe you design them at some point, maybe a few years down the road, they're produced, meaning there's already some number of years gap with which you lost, let's say. You don't know what the workload will be in 3 years. And then it will be in the field for maybe 10 more years, and the workloads evolve during that time, right? So you're designing for the future, but you know only the past, right? How do you predict the future? Tough. Okay, let me see. Actually, workload is one of the 4 areas of discussion that lead a performance presentation into an endless debate. These rat holes and their relative size in terms of time consumed are shown in this figure. As you can see, workload is the biggest thing. Presenting this cartoon at the beginning of a presentation helps to avoid these areas. Okay, maybe we should have this cartoon during presentations. Okay, but if you find this cartoon, you can feel free to bring it up. If you find that the discussion is getting into a rat hole, you can bring it up. And this is his reason. Some of them are actually odd, but I like the last reason also. Why change? It's working okay. This is really the enemy of progress, let's say. It's all working okay. Depends on the definition of okay, of course. There were some other things also. Okay, this is a good place to stop and take a break. And then we're going to talk a little bit more into logistics and how to present things. So let's be back when the bell rings. And hopefully we'll finish early today.
About the new course introduce the fundamental of computer architecture.
Yes.
So it's pretty different than the computer architecture class.
That's true, yes. It's more DDCA-like.
Yeah, my question was, is it inspired from, because I asked you about the course you taught at IEDM, the one where you have to build the processor. I was wondering if the labs are...
No, labs are... so it's kind of a hybrid between DDCA and computer architecture. So if you take in computer architecture,
there's no need to...
Probably not, yeah.
But so I mean, sorry, I'm also taking DDCA now.
Oh, if you're taking DDCA, we'll cover a lot of the concepts. So if you take DDCA plus computer architecture, you're already covering almost all the ground, really. Yeah.
And also, like, for almost, I think they're not accessible now. Maybe.
Oh, okay.
Probably they are, but it's just like you have to.
Some permission.
Yeah.
Okay. There's something wrong then with the access permissions. So okay, I'll tell Konstantin, or you can tell Konstantin or Mohammed, but they're not here right now. Yeah. Sure.
Well, I have a question. So,
sure.
I'm still taking DDCA.
Okay.
It's my second semester.
Okay.
Is it a good idea to take DDCA and seminar simultaneously?
Probably not. That's my guess. Yeah. That would be my suggestion. If you take DDCA, it's going to be much better.
Okay. So you encourage me to take it
next semester, perhaps. Yes, that's my suggestion, because you will learn a lot of fundamentals in DDCA, and then a lot of the concepts will become much easier.
I'll stay today.
Okay, sure. Yeah. Hello.
Just one quick question. In case we would decide not to take the course, not because I like it, but next week I may find that I'm going to be a bit resource constrained for this semester. I would have to sign out by the end of the week.
Yes.
Yeah, just that
I should say that also, and then thanks for reminding me.
If it's by Sunday.
The earlier the better, because there's a long list of other students who may want to take the course, so it'll be better for them to get in quickly.
Yeah, I'm still kind of, because I really like to take it, but I'm still trying to weigh on whether I'll have enough time or not, but,
Okay. The earlier the better.
Yeah, no, definitely. Okay. Thank you.
Hey, Christina. How are you? Things are going well? Yeah, that's good. When is your flight?
I believe for the airport alone.
Oh, okay, so it will be flat. Maybe.
Yeah.
You want to talk about it?
Yeah.
All right. Is everything good online? Yeah. Okay. I assume yes. Okay. Okay, so we covered this. So keep in mind the rattles. There are also some more advice. There's also some more advice on talks. I would recommend people to look at this. I think it's a nice tips from my former colleague K1 on how to give clear talks. And I agree with a lot of these principles that he provides. I think in writing also this is true. Like every sentence matters. The audience prefers not to think. The readers don't prefer not to think. If they think, they may think things that you don't want them to think. Meaning you need to present your results in a way where you draw clear conclusions. This is the key insight to derive out of this result. At least this is the insight that I want to highlight, right? Surprises are bad. Say why before what. In fact, in many cases, I read papers where they jump into the implementation. This is how we implement things. Oh, wait for a while. Before implementing things, tell me why you're doing things the way you're doing it, right? Give me an overview of what's happening and tell me why you chose these design choices, and then go into implementation so that at least I hope I understand things better, right? Yeah, there's a study in psychology where people were presented with a paragraph that explains something with no context. You read the paragraph and most people don't understand anything. Whereas if you actually provide a title that gives the content of the paragraph, they read it with a mindset where they understand everything in the paragraph. This is a real study. It's called Washing Clothes. And the paragraph, actually, this little study is done in early 1950s, actually, late 1950s, maybe early 1960s. The paragraph is about washing clothes. And if you don't have the title, the paragraph doesn't make sense. If you have the title, everything makes sense. Maybe if you search for it, you'll find it. I don't remember the authors at this point. But basically, explaining every figure, graph, or equation is important. That's true in the paper also. Sometimes I read papers where they say, go look at figure 3. and I look at figure 3, I don't understand anything. You need to explain it, right, basically. And when improving the talk, it's good to have the mindset the audience is always right. They may not be always right, but it's good to have that mindset so that you can actually tailor the talk to the audience, right? Okay. Does anybody know who painted this painting? I need to cover the. This is where we don't want that, but anybody can read this far? Okay, Salvador Dali, yes. Is this his best painting? If you know Salvador Dali, you don't know? No, you don't think it's his best painting? Not the most famous. Okay, that's true. Exactly. It's not the most famous, and that's Salvador Dali. This is not him, by the way. He painted someone else, although there's some similarity. Kind of, maybe not. That was young Salvador. And he is probably more famous for this one, right? Like, actually, he's famous for many things, but one of these things that he's famous for, the burning giraffe, as you can see. And this is also older Salvador Dali. So what's my point? Learn the basic principles before you consciously choose to break them. Basically, everybody goes through some, let's say, training. And it's good to learn how to paint this first before you figure out how to paint this. Does that make sense? So there are some basic principles that are not good to break. But over time, I think as you get experience, you can start breaking things. Okay, I like the Salvador Dali example. Okay, there are a bunch of seminar talk examples from past seminars. I think this is one example that somebody over here gave in the past. Some of my students also, as you can see. Actually, some of these are not seminars. This is kind of out of order. I had reordered this earlier. So these are my students. But if you go over here, we'll reorder this. So these are some students who've given talks in the past seminars. So I would recommend you take a look at them. And these are good talks. It's kind of a weird order. So we'll fix it. Okay, so you can learn a lot from what has happened before. So how to participate? Hopefully you come prepared. Read and critically evaluate the paper. If you're, as much as possible, of course. Think new ideas. Bring discussion points and questions. Read other papers if you can. Be critical. Brainstorm. Be open to ideas. And pay attention and discuss and contribute. So if you can participate online before, it's even better. But if you can participate after, that's also fine. And during is, of course, the key part. Yes? How much background do you need for the paper? Like when you're presenting, how much background you include? I mean, it depends on the paper, basically. Yeah, it's going to be very... This is why you iterating over the mentors can help a lot, will help a lot. Because they can help you gauge how much background to include. If you include too much background, you will not have time for the new thing. If you include too little background, nobody will understand anything, maybe. So you'll need to strike a good balance over there. And that's part of the art of presenting. Yes. That's correct, yes. We will try to do 2 per week, yes, that's right. Okay, that brings me. If you are not intending to take this course, please drop it right away as soon as possible, because there is a long waiting list. And I think some of those folks want to take the course. And if you are willing to take the course, don't drop the waiting list right now, because I think there will be some shuffling. Some people will drop and some people will get on the waiting list, get in the course. That's what usually happens in this course. Is anyone on the waiting list here? Okay, maybe they're online or maybe they've already dropped. Okay, but it's good to, if you don't intend to take the course, I would suggest giving the opportunity to someone else. Okay, so we'll go over guided talk preparation. This is kind of an algorithm, basically. You prepare a talk, you first are assigned a presentation date. If that doesn't work for you, you should inform us immediately so that we can reschedule, because that requires changing someone, clearly. You study your papers, you create a draft presentation, and you meet the mentor and get feedback, and you keep iterating, basically, until your presentation. And preparing a good presentation takes time, so start early after you're assigned your paper. And hopefully you'll have enough time after you assigned your paper of course, the earlier people to present are going to be less time. We'll take that into account. But in this, I think this semester, we limited the course to 14 people at most. So we'll start, we'll have enough time, hopefully, for everyone. So read the paper carefully, critically, creatively. Think of improvements, basically. You can read this on your own. I mean, if you can try examples, tools, that's great, actually. And consult with mentors if you have questions. And I think we already talked about the draft presentation. I'm not going to talk about this in detail, but clearly don't present all the details. Don't present too much background, too little background, etc. And this is all art in the end, and you will hopefully get to a good point if you iterate nicely with the mentors. Okay, so mentor, this is the most important part over here that I want to emphasize. You should really have at least 2 meetings, and it should be at least 1 week before the talk. Don't wait until the last day, because that's not going to work. In the past, we've had some students who waited until the last day, and the presentations were not that great, let's say. Whereas people who were more proactive had made better presentations. So meetings are mandatory, so don't take this as optional. And this is actually part of one of the biggest learning experiences that you will have in this course, because it's kind of personalized, and you will be mentored to deliver a good talk. And almost all of these people who are going to be your mentors have delivered talks before in various occasions. Some of them have delivered talks in top scientific conferences, and they will be mentoring you. So it's good to keep that in mind. And somebody else mentored them also in the past. It's good to think about that. Okay, so prepare for the meeting, schedule it early, send slides in advance, because mentors usually look at the slides and prepare and give comments. Write down any questions you may have that you may want to ask the mentors, and make sure you address feedback. This is actually very important. Take notes for the feedback and address it, because if you don't address feedback, then somebody else may have the same issue. Your mentors probably are good at spotting issues, but if someone spots the issue, then someone else may spot the issue when you present it, right? Okay, feedback is important. And if the feedback is, let's say, doesn't make sense to you, then you ask the mentor, like, why did you give this feedback? It's always good to learn the reason. If you do it for everything, of course, then the communication bandwidth will be very high, so it's difficult. So sometimes you need to figure out why the feedback is there also. Okay, grading and feedback. Let's see. I think this is online, right? But let's go over it. Most of the grade will be determined by the quality of your presentation. Like, how well did you understand the material? How well did you present it? How well did you answer the questions from both the audience as well as us? Be prepared to explain things, basically. And we will also take into account the difficulty of the paper. Not all papers are equal. Some of them are much harder. Some of them are easier. And also the time you had to prepare and how you address the feedback. So meetings with your mentors are important in this as well. The other 30%, hopefully you're not here for the grades. Most people get a good grade in this course, more so than DDCA. But I mean, you need to put in some work, clearly. Quality of the synthesis paper is important. It's about 30%, well, 30%. And you will see the synthesis paper. Attendance and quizzes are also important, like 10%. And you can get a bonus if you participate, basically. And I would recommend people to participate so that you can get the 15% bonus. Any questions? Yes. It's basically 1 month after the last day of class, I think. Yeah. And by the way, someone told me that the homework is not accessible online. You may want to check that. Like, they click and they get some permission denied or something like that. Yeah. No, please check. Okay. So we will try to give you a feedback if time permits during your presentation, like strengths and weaknesses. We don't have enough time. Let us know upfront if you prefer not to receive that feedback in front of everyone. Or you can also arrange a meeting to get feedback from your TA or mentor or us. Okay, this is the expected schedule. Hopefully the dates are correct. So we will meet once a week with 2 presentations per session. Next meeting is next week. But until your presentations start, we may actually have some presentations on some research topics, just to cover things. So you learn about more computer architecture. We'll see. Everything will be scheduled dynamically. So once your presentations start on April 9th, there will be 2 presentations per session. And I already talked about the 50 minutes roughly for each presentation. As I said, paper assignment will be done online. Check your email on that one. I already talked about homework 0, so hopefully you'll submit it soon. And homework 1, hopefully you'll submit that soon. And this will come to your email. Okay, I already said all of this, I think. So these are some comments from past students who liked the course. Most people like this course because it's not that hard, let's say. But it is work in the end. It's not maybe as easy as some of the other seminar courses. I think some comments, high investment, high return. I'm not sure if it's really high investment, but okay. I think this is what I mentioned earlier, guidance from 2 top researchers in the field. Yeah. Okay, hopefully you'll you'll like computer architecture after this. Okay, there are some other things that you may want to look at after this if you're interested, but I'm not going to require any of these, so you can take a look. And some of you have taken digital design. So if you want to ever refresh some concept for some reason, like a paper talks about SIMD architectures, for example, usually DDCA is a good place to find those basics. DDCA actually covers a broad range of basics in computer architecture that a lot of papers in the end may reference or build on. So I'd recommend those materials. More advanced, of course, computer architecture course some of you may take has also. Okay, I think this is all I have. Any questions? Everybody's happy. Okay, then we can quit early. So have a nice week and weekend, and we'll see you next week.